Hello everyone. We have started discussion on well log interpretation. We have already discussed some of the methods which we use for porosity calculation from the well logs and how to determine the lithology or how to calculate the different mineral volume percentages or the lithology of the formation with the help of cross plots. Now, the next step in the well log interpretation is to calculate the formation water saturation, the formation water resistivity. We discussed some of the methods which are based on the overlays such as the RWA method or RXO by RT approach, which may be used for qualitative interpretation at the well site itself, or if we have the reliable porosity and the resistivity calculation, they can also be used for the quantitative interpretation as well. Now, the next topic in the well log interpretation is the pattern recognition techniques such as Hengel and the Pickett cross plot, which can be used to calculate both the formation water saturation, the formation water resistivity, as well as some of the other rock and fluid properties. So let's start today's discussion. So these are the topics that we are going to discuss today. One is the Hengel cross plot and second is the Pickett cross plot. So these both cross plots, they are the graphical solution to Archie's equation. So this is our Archie's equation where the formation water saturation, if the value of the saturation exponent is equal to 2, then the formation water saturation can be given as under root of ARW divided by RT into 5 raised to the power m, and these parameters A, RW, RT, phi, m and n can be estimated from different sources such as mud log, coring and core analysis and our well logs. So for example, generally we calculate the value of A, m and n through core data. They can also be estimated from the well log analysis as well, but generally the core methods where we can measure the formation registry factor and the registry index from collected core from the well bore can be measured and in different water saturations, and the value of A, M, N can be computed. The value of RW, as we discussed in the last class, it could be calculated from the water analysis from different well logs as well. And we will continue on the discussion on the formation water resistivity calculation today as well. The value of RT will come from the resistivity logs. Phi will come from our density neutron and sonic log. So let's say if I have a well bore and this is, let's say this is water layer and this is our oil layer, and if I want to calculate value of SW in the oil layers, so I can calculate thereafter afterwards SO as 1 minus SW. So I need all these parameters, value of A, M, RW, RT and N to calculate the value of SW. So in conventional interpretation, you can go on and apply the equation at each depth, each point individually and try to calculate the value of SW. For that, what you need? You need the value of RW, RT, phi, A, M and N at all these points. Sometimes not all of the parameters may be known to you and you might need to estimate the some parameters. So Archie equation can only be applied if you have all these parameters. So let's say if you don't have the formation water resistivity, so either you calculate the formation water resistivity first, then only you can use the Archie equation. The value of m and n may not be known accurately. So in order to calculate these parameters, we must have sufficient number of cores available so that we can analyze in the laboratory. Then only A, M and N can be estimated. Another approach would be to use this Hengel and the Pickett cross plot, where you can calculate the formation water saturation without calculating the formation water resistivity or the porosity first. So in certain cases, for example, Hengel cross plot can provide you formation water saturation by plotting the resistivity data and the porosity data on a cross plot, and you can estimate their formation water resistivity from this cross plot very easily, and you don't have to convert the value of bulk density to porosity before calculating water saturation. So their formation water saturation can be calculated by plotting residue value along with our bulk density values. So can help us in the formation water saturation calculation by graphically solving the RC equation. So let us start the discussion on one of the cross plot. First we will discuss the Hingle cross plot, thereafter we will discuss the Pickett cross plot. So this is an example of our Hingle cross plot. So what we have here, we are going to plot the formation residue data or the RT values along with the porosity values. Instead of porosity, we can also use parameter Ruby and delta T. Also, that means formation bulk density measurement or the travel time measurement from the sonic law. So either these can be converted to porosity and we plot the RT versus phi, or we can directly use the raw values of Ruby and delta T. Also, we can also plot RT versus F. So on a graph paper, we can have RT here and the bulk density here, or porosity here, or F here, and delta T here. In fact, the scale of RT increases in this direction, the bottom direction. So what does it give us? It gives us a family of straight line. So let's say in our well bore, I have a water bearing layer and if I have a oil bearing layer. So if I take the data point from the water bearing layers and oil bearing layers and plot them together on this graph paper, so I will get a family of straight line like this in line of different water saturation. For example, few data points or the data point from the water zone will be on saturation of water equal to one line, and we can also draw the line of different water saturation, such as here 0.25 and 0.5. So all the data points which are on 0.5 line, they will have formation water saturation of 0.5, and all the data points which are on this SW equal to 0.25 line, they will have water saturation of 0.25. So let us see how this plot or this cross plot can be drawn. But first, in what condition we can draw this cross plot? So this cross plot or the Hingle cross plot can be drawn across formation where lithological and salinity changes are absent. That means value of A, M, N is constant. That means all the rock have same lithology, and we have constant matrix density and constant matrix travel time and constant salinity. That means we have constant RW. So formation water residue should also be constant. So that means in a well bore, if we let's say multiple layers, that means same type of formation water is there, same type of lithology is there, so that A, M, N can be constant. We have same matrix density and same matrix travel time. So that means the formation must be clean and liquid filled. So if the matrix density is changing or the cell is present, then cell correction must be applied first, then only Hingle cross plot can be drawn to calculate the formation water saturation. So application, we can estimate the reservoir properties, we can estimate the lithology, and we can also identify potential hydrocarbon bearing formation and calculate the water saturation and oil saturation. For lithology means we can calculate the matrix density from this cross plot, so we can identify whether we have quartz or sandstone or carbonate rocks such as limestone or dolomite. So this is our RC equation. We know that SW raised to power n is equal to RO by RT, or RO can be written as F into RW by RT. So I can put F as here in this equation A divided by 5 raised to power m, and if I rearrange, I can write that RT raised to power minus 1 by m should be equal to SW raised to power n divided by ARW whole raised to power 1 by m into 5. So this equation is similar to a equation of straight line where y is equal to c phi, where y is RT raised to power minus 1 by m. This parameter is our constant c and this is phi. So y is equal to c phi. So if value of c is constant, that means y and phi plot should give us a straight line. So y is what? RT is minus 1 by m and phi is porosity. So So plot of RT raised to power minus 1 by m with porosity should give us a straight line. But is it the value of C is constant? What is the value of C? You can see in value of C we have A term, or W term and M term, which are assumed to be constant for this cross plot. Only variable is, even n is also constant, only variable is SW. That means if the formation water saturation is different, the value of C will be different. So let us take example of an oil zone and water zone. In water zone, SW will be equal to 1 for a water bearing formation or water zone, and SW will be less than 1 in case of a oil bearing formation. That means water zone will have a different line and oil zone will have a different line. So if you plot the value of RT and porosity together, all the points on a water zone will fall on this line, which is called the water bearing line or water trend line or RO trend line or simply the RO line. For other value of water saturation, we will have different lines. Like this is for one water saturation. This is for one water saturation. This is for another water saturation. So this equation is going to give me a number of straight line or a family of straight line for different value of formation water saturation. So you can see this graph is in between RT raised to power minus 1 by m and porosity. So RT raised to power minus 1 by m is increasing in this direction, porosity is increasing in this direction. Now I can see scale here is given as RT. That means this graph is already scaled to the resistivity value. That's why you can see the resistivity values are increasing in this direction. So that RT raised to power minus 1 by m can increase in this direction. So we have a water trend line, and obviously the value of water saturation will decrease, so the slope will also change and it will decrease in this way, so that all the other lines will be below the our water trend line. So this way we can easily identify where is my water zones or where is my water zone, and all the calculations are performed with respect to this water trend line. That means if I want to plot the my Hingle cross plot, I must have a water bearing section in the data point that we are using to prepare this cross plot. If water bearing line is not present, then a hypothetical water trend line can be plotted, but again that will need sufficient number of data about the formation lithology and its rock and fluid properties to plot a water trend line. So if a water bearing zone is present, we can easily plot our water bearing line and further calculation may be performed. Now all the line will go through origin because we don't have any intercept in this equation. Now you can see here it is not going through 0, ideally it should go through from where 0 to 0. That means when RT raised to power minus 1 by m is equal to 0 or RT tends to infinity, and the second point porosity will be equal to 0. So that means our origin point should be phi, that is x coordinate should be 0, and RT raised to power minus 1 by m should be 0 or RT should be infinity. So this is my porosity and RT value on the origin. Because this here it is not going through 0, x is not 0 because this is plotted in terms of bulk densities. That's why it is not going through 0. Now let us see how this cross plot can be plotted in terms of rho b and delta t. So we know that in case of sonic law, the porosity equation is given as phi is equal to delta t minus delta tma divided by delta tf minus delta tma. Again, sometime delta t is also written as delta t log. So delta t means it's the log reading recorded by the tool, or delta t also mean the same thing. Delta tm is the formation matrix travel time, delta t is the fluid time. So I can write this simply. I can separate these two terms. This will be the first term and this will be the second term. So I'm calling this as alpha and this as beta. So this will become what? Phi is equal to alpha delta t minus beta. So y will be equal to c phi, or y will be equal to c alpha delta t minus beta. So you can see alpha and beta are nothing but depend upon the formation matrix travel time and the formation fluid travel time. So c alpha delta t minus beta. If I expand this, alpha and beta here will be constant. So again, I can, instead of plotting in terms of porosity, I will have what? In terms of delta t. So C alpha delta t minus C of beta. So I can plot it like this. So I will have an intercept instead of graph going through 0. Same way I can write the density porosity phi is equal to rho ma minus rho b divided by rho ma minus rho f. I can separate these two terms just like this. These two terms should be separated. So rho ma divided by rho ma minus rho f minus rho b divided by rho ma minus rho f. So again this could be beta and this term could be alpha. So phi will be equal to alpha minus beta into rho b, or y will be equal to c into alpha minus beta into rho b. So again I will have intercept. So what will be my origin point? So earlier origin point was porosity and the resistivity. So resistivity still should be infinite, the y coordinate should be infinite, or the in actual scale RT minus 1 by m should be 0. In case of porosity, when the graph is in between the RT minus 1 by m and porosity, then the origin point is 0. So y is equal to c phi, so both terms should be 0. When I have delta t as coordinate on the x-axis, so in that case the porosity should be equal to 0 when the log travel time should be equal to what? Our matrix travel time. So the origin should be delta tml. Similarly, if I am plotting the graph in terms of bulk density, so when my process should be 0, when I have only matrix. That means the bulk density should be equal to what? Our matrix density of the formation. So this way the plot can be plotted in terms of delta t or rho b, and the origin point can easily be defined or used to locate the delta tma and rho ma. So like in earlier graph, this graph may have been plotted in terms of rho b or delta t. So this is representing what? Our rho ma or delta t ma. So this is the graph paper that we can use for Hingle cross plot. Now you can see this is already scaled in terms of fr is equal to 0.62 divided by 5 into raised to the power 2.15. That means I can use the f also for plotting, I can use phi also for plotting, or I can use the Ruby data also for plotting. On y-axis I can directly input the resistivity values, or it is also scaled in terms of conductivity values. So this is given for a particular a value that is equal to 0.62 and m value of 2.15. So depending upon the a and m values, I can use this graph paper directly instead of calculating the RT raised to the power minus 1 by m then plotting. So it will be easier to directly read the value of formation resistivity from this figure instead of plotting in terms of RT raised to the power minus 1 by m. So let us take an example and see how the interpretation of Hingle cross plot can be done. So for example, this is a synthetic data set which is consisting of the point from an oil bearing formation and a water bearing formation. For different depth, value of bulk density is given and the resistivity is also given. So either I can convert the bulk density to porosity to plot the cross plot, or I can directly use the bulk density as well to do the cross plot. The beauty of doing the cross plot in terms of Ruby and the resistivity is that we can calculate the matrix density of the formation. Now, matrix density of formation can be calculated if it is not known from the Hingle cross plot. So this method provides one of the source to calculate the matrix density. Once again, the matrix density is best estimated from the core data. If you have good core data available, or you have taken a number of core sample which are from the same representative depth from where you're trying to do all this cross plotting and the calculation, then the core derived matrix density is always the best estimate of our matrix density. But if the core data is not available, you can also use the matrix density derived from our Hingle cross plot. In fact, in such cases, this is generally used to estimate the matrix density as well. So what we have to do, we have to prepare the cross plot. We have to the information is given as that this well bore is drilled through a series of limestone formation. That means rho must be around 2.71. So we have to calculate the metric density, we have to calculate the water saturation and formation water ratios as well. So first step is to plot the each data point from the different zone. So you can see I am already plotted in terms of RT raised to power minus 1 by m and the bulk density. So I have taken here m as 2. M is assumed to be 2. If it is already known, you can use that value of m. So for this example, I am assuming that the formation have a cementation factor of m is equal to 2 and a is equal to 1. So I have plotted all the data points. I have calculated the RT is minus 1 by m and the bulk density. You can see all the data points are plotted. So this is how it would look like on RT is minus 1 by m and the bulk density graph. We could have also used the customized graph. For example, here I have used the value of a is equal to 1 and m is equal to 2. So I could have also used this customized graph where I can directly input the value of residuity along with the bulk density. So it would be easier if you're doing the manual interpretation or doing this graph or you're plotting this graph manually to directly read the value from the RT and rho b from this graph and plot them instead of calculating RT raised to minus 1 by m, which I have done it. Nowadays we use computer for this cross plot. The manual interpretation is not done, so you may not need to use this graph paper. Instead of, you can directly calculate the value of RT raised to minus 1 by m and find to do the cross plotting. So second step is to draw the water trend or arrow trend line. So which points are belonging to water bearing formation. So I have to draw the water trend line and the arrow trend line. So you can see this is my arrow trend line, because we have discussed that point from the water saturation will be falling on the farthest line in this direction, because there SW is equal to 1. So in this data set you can see almost all of the points are falling in a straight line. So I can draw a regression line and intercept on the x-axis to estimate the value of rho ma, because at this point the value of porosity will be equal to 0. So I have identified my water bearing points or water bearing formation by drawing this water trend line. So I can now easily see on this graph where my water bearing zone exists. In reality, you will have a number of points like this. All the points will not fall on a single straight line. You will have a cluster of data points, and those data points could be identified as a water bearing trend, and a best fit line could be plotted to find the value of rho ma. So this way my water bearing trend line can be plotted. So in this example, if you can see here, the value of rho ma is approximately coming as 2.706754 or 2.71 gram per cc. Again, the formation was limestone. You can see we are also getting matrix density almost same as our limestone matrix density. If we have used the delta T instead of rho b, I would have calculated what? Delta T ma. Now next step is first calculate the formation water resistivity. We can, so this is our equation for value of SW equal to 1, or in case of water bearing formation, this equation will become RO raised to power minus 1 by m equal to A into RW raised to power minus 1 by m into porosity. So this is nothing but now becoming graph between what? The water trend line. It is a graph between RO raised to power minus 1 by m and porosity and a constant C. The value of C is equal to A into RW raised to power minus 1 by m, which will be constant for constant lithology and formation water salinity. So y coordinate should be RO on a water trend line and S coordinate should be phi. Phi I can convert to F also, and then I can use this equation to calculate formation water resistivity. So like this coordinate on y axis should be equal to RO, and here it should be rho b. If I have plotted in terms of bulk density, which can be converted to porosity and can be converted to F. So then I can use this equation RW is equal to RO by F. For example, I can take any point on this trend line. So In reality, what we have, as mentioned, that we have a cluster of data point. Don't take any point within the cluster of data. First draw the best fit line and then take the point on the from that best fit line to calculate the value of formation water resistivity. Otherwise, if one data point is here, one data point is here, you will get different RO and different phi, so that you will get different formation water resistivity. So we are doing what? In a way, you are averaging the formation water saturation by drawing this water trend line. So because of the statistical variation in the measurement of RT and the porosity or the bulk density or the formation travel time, you will not get all the data points in a single very good straight line. There will be a cluster data point from which you have to draw the best fit line. So if you calculate this way, if you find the coordinate of, let's say I'm taking, like in this case, 0.3 is exactly on the this straight line, so I'm taking the value of the point data from the 0.3. First I've calculated the 5 values, and RO I read from the this log, it is coming as 16. Then I have calculated the value of F, and if I calculate the value of RW, it is coming somewhere 0.0268 ohm meter. So this way formation water resistivity has also been calculated. Now next is to calculate the water saturation of all the other points. So now what I have on this cross plot, I have a straight line which is called a RO or water bearing trend line. That means these points are belonging to a water bearing formation. Other points which are not falling on this water trend line should belong to a hydrocarbon bearing formation where value of SW is less than 1. So I can calculate the formation water saturation at all these individual points. For example, let's say this point 10, where we have certain value of porosity and the resistivity. So I can draw a vertical line and go up towards the water trend line and find this intercept point. So this rock has particular porosity as indicated by this point. If I go up and this point on the water trend line, it has also the same porosity. It also has same A, M, N and RW. That means this rock defined by this point and this rock defined by this point is same because of same lithology and same formation water salinity and same porosity. Only thing is that here we have both water and oil, and when I move up and find this point on this water trend line, this has same rock but now I have only water. That means oil at point 10 is replaced with formation water at this point. So this point RO value or the resistivity value will be the RO value of this point. So now for point 10 I have both RT as well as RO value. So I can calculate SW is equal to under root of RO by RT if I have value of N that is equal to 2 in this case. So to summarize what we have a water trend line which depends on all the water bearing data points. Any other point which is not on the water trend line, that should represent a hydrocarbon bearing formation point or a hydrocarbon zones. And at each point I can calculate the value of RO by going up and finding the intersection on the water trend point, and then I can calculate the formation water saturation using this equation. Also, I can draw the different water saturation line as well. For example, SW is equal to RO by RT. So what will be the value of SW for different RT by RO ratio? At when RO is equal to RT, that means we have a water bearing zone, that means SW is equal to 100%. At different value of RT by RO, when RT is 1.23 RO, then the water saturation will come as, according to this equation, 90. Same way, different ratio, I have calculated the formation water saturation. So for 80, 70, 60 and 50, what are my ratio of RT by RO? So what I can do is that in this cross plot, again, this point is my RO point. So let's say this point. I need to move, this is for what? 0.5 water saturation line. So I know that RT by RO is equal to 4, then only water saturation will be equal to 50%. So I will move this such that this point resistivity values is equal to 4 RO. Similarly, for 40%, that means this point, it have RT value of 6.25 RO. So I have determined the point of different water saturation. So once the water saturation of any point in this our equation y is equal to C5, only variable in C was water saturation. For different water saturation, we'll have different value of C. So as W equal to SW1, then we will have a constant C1 which will be constant. For SW2, we will have a constant C2 and so on. That means I would have a number of line of constant water saturation. So this line can be drawn from this point which will go through origin, because again y is still equal to C5. All the point will start from the same origin. In case of bulk density, you would have rho ma and RT is equal to infinity. So this way, once I have determined the point, I will draw a number of straight line like this, which will represent the different water saturation lines. So now I have a graphical solution on my hand. I can directly look at the value of all this water saturation on different line, and I can see which points are falling in which zone. For example, point 2, it has location between the 0.5 water saturation and 0.4 water saturation line. That means its saturation must be somewhere between 0.4 and 0.5. And let's say 0.6, it is below the 0.4 and above the 0.3. That means water saturation will be somewhere 0.3 to 0.4. So even if I have not calculated the value of RW or phi, I would have easily plotted all these water saturation line and I could have calculated the formation water saturation. So even if rho ma was not known to us, I would have done this cross plot. So think about it. If I needed to do the water saturation calculation from the RCH equation, I must have the value of phi. If I don't have value of rho ma, I cannot calculate value of phi. Then I cannot use the RCH equation. By plotting this graphically, we estimated the value of formation matrix density or rho ma, and we also solve for the water saturation calculation. So some parameter which were not known to us earlier, now we have calculated. So I can also enhance my understanding of my solution. I can draw the map which shows my potential hydrocarbon zone. For example, let us say if I define cutoff porosity to be greater than 9% and water saturation to be less than 50%. So this is my cutoff water saturation line where the water saturation is 50%, and this is my cutoff porosity line where my porosity is 9%. So that means greater than porosity 9% and less than 90% saturation. So all the point in this zone should belong to my potential hydrocarbon zone where I have sufficient quantity of hydrocarbon which could be produced because I have good porosity and good oil saturation. So here I have good porosity and good oil saturation. That means sufficient quantity of oil is there because of high porosity and high oil saturation, and because we have good porosity, good permeability could also be expected. For example, if I have take this point have low oil saturation. This point 11, it has low oil saturation. This point 4 also have low oil saturation. Point 1 probably have very good oil saturation, but it has low porosity. So overall reserve could be less. Also, it would have less permeability also. That's why this is not in our potential hydrocarbon zone, which should be perforated to produce the reservoir. So let us take an example, field example of this. You can see this is a field example where we have plotted the data, and you can see the data from 3 depth interval have been plotted, which can easily be identified on this cross plot. So blue points are at a depth of 4980 to 5110 feet, and then pink and red point are at different depth. So you can see we have 3 clusters. One is this red cluster, second is you can see the pink cluster, and then we have a blue cluster data points. Because all the zones have different water saturation. So a water trend line have been drawn. You can see this is my water trend line where SW is equal to 100%. Matrix density have been estimated as 2.66 gram per cc. That means the formation is most likely to be our sandstone. The graph was also prepared in terms of our travel time. Delta TMA has been estimated around 55 microsecond per feet, which is again agrees with the value of Rome, that is it is most likely to be a sandstone formation. Now you can see two water saturation line which are less than SW equal to 1 have been also plotted. So this is my SW equal to 25% line. This is SW equal to 50% line. That means you can see the hydrocarbon zones which have saturation less than 25% are considered here in this reservoir. So where water saturation is less than 25%, those points are considered as our hydrocarbon zone in this Hingle cross plot. So you can see the beauty of this cross plot. All my formation data are in one place. They are grouped together by depth interval. So you can read from this cross plot what is my depth of hydrocarbon bearing formation, what is my water saturation and oil saturation and porosity in my hydrocarbon bearing formation. So the solution of a well log interpretation can be printed in a single place and you can directly visualize what is there inside my reservoir. So this way Hingle cross plot can be prepared and we can calculate the different properties as discussed in today's lecture. So today we discuss what are the different cross plot which can give us the a graphical solution of RCH equation. So Hingle cross plot has been discussed. In next class or in the next lecture we will discuss our Pickett cross plot and there we'll discuss how this cross plot can be used to calculate the value of M, the value of RW and the formation water saturation. See you in the next lecture.